Hello everyone. In this chapter, we'll be learning about the wave behavior of light. So at the end of this lesson, you should know that electromagnetic waves are transverse waves made up of mutually perpendicular oscillating electric and magnetic fields. And oscillating charge produce electromagnetic wave of the same frequency as the oscillation, and electromagnetic wave causes charges to oscillate at the frequency of the wave. So what does this mean, right? So let's first of all go through the first point, all right? What is a transverse wave? So basically there are two kinds of wave. One is a longitudinal wave and the other one is a transverse wave. So to differentiate between a longitudinal wave and a transverse wave would be basically imagine if a particle on a longitudinal wave, the displacement of the particle will be along the direction of propagation of the wave. So let's assume, right, that the wave is propagating from left to right. So imagine if there's a particle here, how is it going to vibrate? It's going to vibrate from left to right along the direction of the wave as the wave propagates from left to right. On the other hand, if there's a particle here, when the wave propagates from left to right, the particle is going to experience a displacement that is vertical along the vertical direction that is perpendicular to the direction of propagation of the wave. So that's how we differentiate between a longitudinal wave as well as a transverse wave. So electromagnetic wave are basically a transverse wave. All right. So the oscillation of the electric field and magnetic field are along the vertical, whereas the propagation of the wave is along the horizontal. Okay, basically an accelerating charged particle generates electromagnetic wave. So let's consider a dipole antenna. So this dipole antenna is connected to a signal, right? And this signal actually generates alternating current. So when this generates alternating current, the alternating current is going to cause electrons to move up and down this dipole antenna. So when the charges move up and down, the charges are oscillating. And in the process, when the charges oscillate, they are going to generate electromagnetic wave, like what we see here. So the blue line here represents the magnetic field, and the red line represents magnetic field. So the magnetic field is perpendicular to the electric field. So as the wave is generated, it's propagating out. It's like when I'm talking, as I generate the wave are propagating outwards from me, right? So you can hear me, although you are at a certain distance away. Okay, so what actually happens will be when the wave is generated, this is the electric field that is generated. So a dipole antenna is basically an antenna that is made of two poles, all right? Can you see there's one pole here and there's another pole here. So this is known as a dipole antenna. So a dipole antenna will generate electromagnetic wave. And what you see here is the electric field, right? So it is a transverse wave because the electric field is perpendicular to the direction of propagation of the wave. Okay, this red line represents the magnetic field. So you see that the electric field is perpendicular to the magnetic field. So if the electric field lies along the Y direction, the magnetic field lies along the Z direction, and the direction of propagation of the wave is along the X direction. Okay, if we see from here, when we see light, so light is actually an electromagnetic wave. So when we see light, what we will see will be the electric field that lies along the vertical direction, as well as magnetic field that lies along the horizontal direction. All right. Okay, this here is a transmitting antenna, a transmitting dipole antenna. And this here is a receiving dipole antenna. Like how you listen to your favorite radio station, all right? So there's a transmitting station which transmits signals, all right, in the form of electromagnetic wave, and your radio in your car receive that signal. So your car also consists of a dipole antenna. So when the wave, all right, so in this case, all right, what happens is the radio station will generate a sound, all right, or basically a signal, and the signal is an alternating current. So this alternating current will cause the electrons in the transmitting antenna to vibrate. So when the electrons in the transmitting antenna vibrates, it's going to generate electromagnetic wave. So electromagnetic wave consists of electric field, the blue one, and the magnetic field that is represented by the red sine function. Right? It looks like a sine function. So when this wave propagates, whenever it reaches your receiving antenna, this electric field that strikes the receiving antenna is going to cause electrons in this receiving antenna to start vibrating. All right. So this is what is represented by the outcome, right? That is the oscillating charges produce electromagnetic wave. So this is what is described in your transmitting antenna. When the charges oscillates inside the transmitting antenna, it generates electromagnetic wave, where the frequency of this wave is the same as the frequency of oscillation of the charge inside the transmitting antenna. So if I say that these charges are oscillating at the frequency of 50 hertz, then it's going to generate electromagnetic wave of 50 hertz. All right, so the frequency is the same. So the next point will be when this electromagnetic wave strikes a receiving antenna, all right, a receiving dipole antenna, this electromagnetic wave is going to cause electrons in this receiving antenna to start vibrating. So this is what is represented by the second line, all right, that is electromagnetic wave causes charges to oscillate at the same frequency of the wave. So when this wave strikes your receiving antenna, the electrons are going to vibrate. So the frequency of vibration of the electrons is the same as the frequency of the electromagnetic wave. And the frequency of electromagnetic wave is the same as the frequency of the electrons in the transmitting antenna. So basically the frequency that you receive is the same as the frequency that is being transmitted. Okay, electromagnetic wave is actually a very wide spectrum. Okay, we use electromagnetic wave a lot in our everyday life. So electromagnetic wave consists of low frequency radio waves, like transmitting of radio signals, all right, TV stations and so on, right? These are basically making use of low frequency electromagnetic radiation. Microwave oven uses electromagnetic wave that is in the region of 1 centimeter, right? That is your microwave radar, all right? And humans, all right, our eyes are only sensitive to a very small part of the electromagnetic spectrum. So our eyes, all right, perceive white light, right? So white light consists of just a very small part of your electromagnetic spectrum. And humans are basically emitting heat. So we are actually emitting infrared radiation, right? So you have visible light. Infrared radiation is basically heat, ultraviolet radiation, right? X-rays that's used mainly in medicine, right? And gamma rays that is basically produced from radioactivity. Okay, next, the outcome will be relate the orientation of the receiving antenna to the plane of polarization of radio or television waves. And the second point will be use frequency of oscillation of the electrons in the transmitting and receiving antenna to explain the transmission and reception of radio and television waves. Okay, this is your transmitting antenna, like what I showed you just now, and this is your receiving antenna. So the transmitting antenna can be a few hundred kilometers away from your home, right? So the radio station or TV station will transmit a signal which in the form of alternating current, through a dipole antenna. So electrons in this dipole antenna is going to start vibrating. So when electrons vibrate, the electrons are accelerating, and this will cause electromagnetic wave to be generated. So when the waves are generated, they are actually propagating out at the speed of light. So although you are a few hundred kilometers away, you can almost instantaneously receive the transmission from a radio station or TV station. So when this electromagnetic wave strikes your receiving antenna, this electric field is going to cause electrons in your receiving antenna to start vibrating. And when that happens, a signal will be generated. So the frequency of this receiving signal is the same as the frequency of your electromagnetic wave. And the frequency of electromagnetic wave is the same as the frequency of your transmitting, the signal in the transmitting station. Okay, now we'll be learning about polarization. You see, in order for us to receive signal in the transmitting antenna, the dipole antenna must be in the same plane as the transmitting antenna. So you see, right, the transmitting antenna is placed along the vertical plane. You see, this here lies along the y-axis. So for us to receive signal, the receiving antenna must also be placed along the vertical plane, the same plane as your transmitting antenna. If we rotate the transmitting antenna, if we rotate the receiving antenna along the horizontal plane, from here, from along the vertical, now it's placed along the horizontal, what happens is there's no signal, all right, picked up by the receiving antenna. So the electric field, all right, that lies along the vertical has got to cause electrons, right, in the transmitting antenna to vibrate along the vertical direction. So this electric field that lies along the vertical cannot cause electrons in the receiving antenna to vibrate because now the electrons are placed along the horizontal plane, right? So electromagnetic waves are plane polarized. So basically, a transmitting dipole antenna will emit plane polarized electromagnetic waves, right? So these EM waves are plane polarized. So polarized means that the electric field only lies in one plane. So a plane is basically a two-dimensional area, right? So like this board, right, is basically a two-dimensional area. So we can consider this board, this white board, right, is basically a plane. It lies along the X and Y. So you see electric field lies along the vertical plane. Okay, what happens is if we look at polarized wave, right, we can see that the electric field only lies along the vertical plane, right, along the Y direction. That's what you see. So in this case, you see polarized electromagnetic wave. If the wave is not polarized, then it will look something like this. Or what you see will be, you find electric field that lies along the vertical direction, and you also find electric field that lies along the horizontal direction, along the Y and the Z axis. So the wave is propagating along the x-axis. So you find electric field along the vertical and electric field along the horizontal. In this case, it is vertically plane polarized. Okay, so where do we apply this, right? So if you look at homes, right, around the countryside, you find that there is this antenna, right? So they have this dipole antenna that is pointing towards a receiving station that can be, a transmitting station that can be a few hundred kilometers away, right? So when the signal is transmitted from the transmitting antenna, this electromagnetic wave will strike the receiving antenna that's located in your home, and this receiving antenna will receive the signal, and then the signal will be amplified by your TV set to get your favorite TV program. Okay, this is where you have horizontal and vertical plane polarized, like country and city channels. So basically, right, if the transmitting antenna is transmitting along the horizontal plane, then what you do is you use a horizontal antenna to receive the horizontal plane. If city channels is transmitting along the vertical plane, then you use another antenna that is aligned along the vertical direction to receive city channels. So the reason why we have two planes of polarization is so that the two channels, that is country and city channels, do not interfere with one another. All right. Okay, let's try this question. So pause the video for 2 minutes. And once you have done this question, continue with the video and find out what is the answer. All right, so basically in this question, the source of unpolarized light is viewed through two cross-polarizing filters, X and Y. So the polarizer of X is placed along the horizontal plane and the polarizer Y is placed along the vertical plane. So we asked to describe the electric field at B and C. So at A, right, you have unpolarized light, limits there's electric field that lies along the vertical and there's electric field that lies along the horizontal. So pause this video, spend 2 minutes, and then once you are ready, continue with the video. Okay, what would we see at point B? So point B is the electric field consists only of the horizontal component, right? Why? Because this is your electromagnetic wave, right? Can you see the electromagnetic wave that is unpolarized? When it strikes the first polarizer, so the first polarizer is placed along the horizontal. You find, right, that the vertical component will be blocked, whereas the horizontal component will pass through, right? So this horizontal component will not be blocked by the horizontal polarizer. So what you see at point B will just be electric field that lies along the horizontal. Okay, the next thing, what would you see at point C? You see this electric field now that lies along the horizontal will strike the second polarizer. But the second polarizer is placed along the vertical direction. So what happens is, you don't detect any electric field, right, at point C. And the reason is because when the wave comes in, that's placed along the horizontal, when it strikes the second polarizer, the vertical polarizer will block the horizontal electric field. Okay, so like what you see here, there are two polarizers, right? The first polarizer is placed along the vertical. The second polarizer is placed along the vertical as well. So you can see the image, right? Okay. So what happens if I rotate the second polarizer and place a second polarizer along the horizontal? Okay, in this case, we don't see any image. The light is totally blocked. So the first polarizer blocks light along the vertical. So only horizontal component passes through. And the second polarizer then blocks the horizontal component because the polarizer is placed along the vertical direction. Okay, let's go to the next section. All right, the speed of a wave. All right, so what's the speed of a wave, what's its frequency, and what's the wavelength? And they're actually related by this formula. Frequency is v, the speed of the wave, divided by lambda. So frequency would be how many complete oscillations does a wave make in 1 second. All right, that is known as frequency. V will be how fast the wave is traveling. So if we deal with electromagnetic waves, then V will be known as the speed of light. And lambda is the wavelength. Okay, what is one wavelength? So one wavelength, or lambda, right, is the adjacent distance between 2 points that are in phase with one another. So let's look at this point, right? The red dot and the lavender dot, all right? So these two red dots are in phase with one another. You see, when the first red dot is going down, the second red dot goes down with it. And vice versa, when the red dot is going up, the second red dot goes up with it. Same case for the lavender dots, right? So these 2 points are in phase with one another. These 2 points are in phase with one another. So 1 lambda is basically defined as the distance between 2 points, 2 adjacent points that are in phase with one another. All right, so this is known as 1 lambda. So frequency would be referred to as the number of complete cycles in 1 second. So let's assume, right, from this point to this point represents 1 second. So the question is, how many complete cycles does it take in 1 second? So how many complete cycles? We can see it takes from here to here is 1 complete cycle. From here to here is 2 complete. And then here to here will be 3 complete cycles. So basically, in a 1 second time interval, this wave makes 3 complete cycles. So in other words, this has a 3 Hertz frequency. Okay, let's try this question, right? So let me explain. So the graph below shows the variation with time t of the displacement x of 2 progressive wave, right? P and Q passing at the same point. So the speed of the wave is 20 centimeters per second. So in A, right, determine the amplitude of P and Q. B, the frequency of the waves, P and Q, and the wavelength of the wave, both P and Q. So solve this for 3 minutes. Once you have done, you can continue playing back the recording. Okay, for E, right, what is the amplitude of P and Q? So amplitude for P will be 3 millimeter. That means amplitude, right, we take it from this point and it goes up to a maximum of 3 millimeter. So amplitude of wave P is 3 millimeter. And for wave Q, the amplitude will be from this equilibrium point, goes up to a maximum of 2 millimeter, right? You can see that. So the amplitude of P is 3 millimeter and the amplitude of Q is 2 millimeter. So B, what's the frequency of the waves? What's the frequency of B and what's the frequency of Q? Okay, frequency is, okay, before that, period. What's period? Period will be the time taken for the wave to make 1 complete cycle. So let's look at this. From this point, right, to this point is 1 complete cycle. Can you see that? From here, goes up, it comes down, and then it starts all over again. So it takes 0.6 seconds for 1 complete cycle. So in other words, this represents the period of the wave for P. For Q, if we start from here, 1 complete cycle will be from here, it goes up, comes down, and then it starts all over again. So 1 complete cycle takes 0.8 minus 0.2 is the same as 0.60 seconds. So basically for P and Q, both of them have the same period. So to find the frequency will be 1 over period. In this case, the frequency will be 1.67 Hertz for both P and Q. So what does this mean? It means that in 1 second, P will make 1.6 complete cycles, right? That is what it means. The same case for Q. It makes 1.67 complete cycles per second. Okay, C, what's the wavelength of the wave? Okay, for C, right, we have to calculate using this formula. Lambda is V divided by F. Do not make the mistake that say, oh, okay, what is 1 lambda is the distance from this point to this point, right? But this here is actually seconds. It's not in terms of meters. So this here, the distance, right, this is not basically distance, it's actually the time, right, is not representing 1 lambda. So to find lambda, we have to use the wave formula, lambda, which is V divided by F. V is how fast the wave is moving, change it to meters, and the frequency is 1.67 Hertz. So lambda will be 0.12 meters, right? Okay, The next outcome will be monochromatic light. So monochromatic light is light that composed of a single frequency. So most light sources emit wave that radiates in all directions away from the source. So the question is, what do you mean by monochromatic? Okay, let's look at this. Mono means single. Chromatic means color. That means monochromatic light is basically light of a single color. So another way to represent it will be light of a single frequency or light of a single lambda. Right? So the better terms to represent monochromatic will be light of a single frequency or also light of a single lambda. So coming back to this example, is P and Q monochromatic? So to answer that, we have to see, do they have the same frequency? If they have the same frequency, then yes, they are monochromatic light. So you go back to exercise 2 just now. Wave P has a frequency of 1.67 Hertz and wave Q has a frequency of 1.67 Hertz. So in other words, both P and Q are monochromatic. All right, so that's the end of part 1.